welcome you in the lecture series of Basics of Communication Engineering. It is 26th lecture of this series. In previous lecture we have discussed about different line coding schemes as unipolar line coding, polar line coding and bipolar line coding. In this lecture I would like to discuss about special purpose line coding scheme, scrambling techniques, and we will also discuss about digital data to analog signal conversion techniques. And the outline of this lecture are special purpose line coding. These are two binary, one quaternary, and 8B60, 8 binary, 6 ternary. And after this, we will discuss about scrambling, B8ZS bipolar with 8 0 substitution, and HDB3 high density bipolar 3 zeros. And after this we will discuss about digital to analog signal conversion, where these techniques are amplitude shifting, frequency shifting and phase shifting. But in this lecture we will discuss only about the ASK. And here the combination of ASK and PSK, it is known as quadrature amplitude modulation, and we will discuss about this in the coming lectures. So and in the objective of this lecture, you will able to explain basic concept of digital data to analog signal conversion. So first of all, we will discuss about a special purpose code 2B1Q, 2 binary, 1 quaternary. Here you can see this is another type of coding. If we are having a rule where 00 is represented by -3 voltage level, and 01 is represented by -1, 10 is represented by +3, and 11 is represented by +1. So they are basically four voltage levels, and these are represented by 1 voltage level is represented by 2 bits. And here you can see with this you can have the modulation rate D. It will be R data rate by the number of bits per signal element. And here you can see this R is equal to D log to L, or you can say here L is 4. So 4 voltage levels are used here, +3 -1 +3 -3, here -3 -1 +3 +1, 4 voltage levels, so L is 4. So from here you can find out that R is 2D. So we see that by using this multi-level encoding, we are able to send more data with less number of signal elements. And in other words, with lesser baud rate, your data rate is more, and because of a large number of signal levels, it will be more prone to errors, and SNR is better in this case. And another type of is the 8B60, 8 binary, 6 ternary, and it is used in 100 BASE 40 cables. And another is multi-transition 3 levels, MLT, and this scheme uses 3 levels, plus V, 0 and minus V, and 3 transition rules are moved between these levels. So if the next bit is 0, then there is no inversion, means if you are on the level 0, then next bit is 0, then you will stay on the level 0, there is no inversion. And if you are on the minus V, then you will be stay on the minus V, and if you are plus V, then you will stay on plus V if the next bit is 0. And if the next bit is 1, and the current level is not 0, means if you are at plus V or minus V, then the next level is 0. And if the next bit is 1 and the current level is 0, in this case then the next level opposite to the last non-zero level. So if the last non-zero level is positive, then next level is negative, and if the last non-zero level is negative, then the next level it will be positive. So based on this you can see here this is 0, and here you can see this is level 1. So the next level is 1 and the current level is 0. So if I start with the positive, this is for the positive for the 1 bit 1, and here if the here the next bit is 0, so for the next bit 0 there is no inversion, you can say, so you will be stay on the positive, and here the next bit is 0, so there will be no conversion, and at this point the next bit is 1 and the current level is 0, so the next bit it will be the opposite to the last non-zero level, so here last non-zero level is positive, so for this one the level will be negative, and for 0 there will be no inversion, and for 1 next bit 1, so here you can see this level it will be the opposite to the previous non-zero level, so it will for this one this is positive v, and for 0 there will be no inversion, so this is the multi-transition 3 levels coding scheme, and the MLT3 is suitable choice when we need to send 100 Mbps data. Now next is scrambling scheme, biphase schemes Manchester and differential Manchester that are suitable for dedicated links between stations in a LAN are not suitable for long distance communication because of their wideband requirement, and bipolar AMI encoding, on the other hand, has a narrow band and does not create a DC component. However, a long sequence of zero upset the synchronization, and if we can find a way to avoid a long sequence of zeros in the original stream, we can use a bipolar AMI for long distance, so we are looking for a solution that is suitable for long zeros level pulses with a combination of other levels to provide synchronization, and one solution is the scrambling. We modified the part of AMI rules to include in the scrambling, and two common scrambling techniques are here: bipolar with 8 zero substitution and high density bipolar with 3 zeros. And first B8ZS, this is particularly used in North America. In B8ZS, whenever you have 8 zeros, then it is being replaced by the following encodings, and a sequence of 8 zeros is replaced by 000 plus minus 0 minus plus, or you can say 000 VB 0 VB if the previous pulse is positive. So if the previous pulse is positive, you will replace 8 zeros by 30 plus minus 0 minus plus, and a sequence of 8 0 is replaced by 000 minus plus 0 plus minus, or you can say 000 VB 0 VB if the previous pulse is negative. Here basically V is the violation and B is the bipolar, that is non-zero level is according to the AMI rule. So here V means there is a violation of the AMI rule, and B means this will follow the AMI rule, and this should be done at the transmitting end and also the receiving end. So it is some kind of a protocol that is being followed by both sides of the communication, as long as the number of zeros does not exceeds 8. As long as the number of zeros does not exceed 8, then there is no problem. When it is 8 or more, then 8 zeros are replaced by this code, and you can see in this code there are 8 zeros, 1 0 0 0 0 0 0 0. So here you can see the previous level is positive, so this is replaced by 0 0 0. Now the AMI rule is violated, so there should be minus, but we will start with 0 0 0 plus minus 0 minus plus. So based on this rule we will have this type of digital data. This is for voltage level plus V for bit 1, and 0 0 0, then voltage level plus V, and this is voltage level minus V, and this is 0 and voltage level minus V, and then voltage level plus V. And if the previous level is negative, then we will have 0 0 0 minus plus 0 plus minus if the previous level is negative. See here V is the violation and B is according to the AMI rule. Now HDB3, high density bipolar three zeros. This is another alternative which is used in Europe and Japan, and it replaced a sequence of four zeros by a code as pre-rule given by in table, just like polarity of the preceding pulse. If the polarity is preceding pulse is negative and the number of bipolar pulse is ones, since last substitution it is odd, then this is replaced by 0 0 0 minus. And if the polarity of the previous pulse is negative and the number of bipolar pulses are even, then it is replaced by plus 0 0 plus. And if the polarity of the preceding pulse is positive and the number of bipolar pulses are odd, then it is replaced by 0 0 0 plus. And if it is even, then it is replaced by minus 0 0 minus. So just like you can see here, you can see if we have data, this is 1 1 0 0 0 0 1 0 0 0 0 0 0 0 0 0. So here we can see these four, 1 2 3 4, four zeros will follow the rule. And here you can see, here the previous pulse is positive, this pulse is positive, and here you can see the number of bipolar pulses, number of ones up to this are 2. So here we will replace this by, because these are even, and for according to the rule it is replaced with plus 0 0 plus. So this is plus 0 0 plus b 0 0 b. This is according to mi, because this is minus and we have the pulse at plus, but here this should be minus, but we are having plus according to HDB3 rule. So this is the violation of AMI rule. And next here you can see up to this, point they are, if this is represented by 1, because according to AMI rule the represented opposite to the previous. So this here you can see 1 2 3 4 and 5. So this is odd, and for this odd you can say that according to rule it is represented by 0 0 0 minus. So it is 0 0 0 then minus. And now again here you can see this is even, so it is represented by plus 0 0 plus. So this is the HDB3 rule. Now characteristic of B8ZS and HDB3, it has three levels, plus, 0 and minus. No DC component is there, and it has good synchronization. Most of the energy is concentrated around the frequency equal to the half data rate, and well suited for the high data transmission over long distance. And this is the spectrum density of various encoding schemes for the NRZ-L and NRZ-I. This is the spectral density as we have discussed in the previous lecture, and this is the spectral density for AMI and pseudo-ternary, and this is the spectral density for the B8ZS and HDB3, and this is the spectral density for the Manchester encoding. As we see, the spectrum of B8ZS HDB3 is good. It allows the transmission through a medium with less distortion and attenuation, because it will match perfectly with the most of the band pass nature of the transmission medium. With this we now change our gear and move from digital data 101 to analog signal conversion. There are many situations in which we have to convert a digital data to analog signal, because we have to transmit the signal through a analog transmission medium. And analog transmission medium means it is a baseband, and a baseband in nature, and there are many other advantages of this analog system. That is, for example, the analog medium, a telephone line. If we want to use the telephone line for the transmission of data, then we have to convert it into analog signal, and this is the basic for the digital to analog signal conversion. And you can see if the input, at the input of digital to analog signal conversion, there is digital data 1010 form, and at the output of the digital to analog converter we will get the signal like this. This is the analog signal for signal for bit 1 there is a carrier, and for bit 0 there is no carrier. This means we are we are sending the signal when there is bit 1, and we are not going to send the signal when there is bit 0. So this is the basic concept behind digital to analog conversion. Digital to analog signal conversion techniques are also known as digital modulation techniques. Digital modulation techniques provide more information capacity, high data security, quicker system availability with the greater quality communication. And there are many types of digital modulation techniques, and also their combination depends on the need. And these techniques are amplitude shift king ASK, frequency shift king FSK, and phase shift king PSK. And the combination of ASK and PSK is known as quadrature amplitude modulation. Now, first of all, we will discuss about amplitude shift king ASK. ASK is a type of amplitude modulation which represents the binary data in the form of variation in the amplitude of the signal. This technique is also known as binary ASK technique. Here the amplitude of the carrier signal is varied to create a signal element. Both the frequency and phase remains same while the amplitude changes. The BSK is also known as on-off king. The peak amplitude of one level, that is 0, is and the other is same as the amplitude of the carrier frequency. So for the bit 0 the amplitude will be 0, and for the other the amplitude will be equal to the amplitude of the carrier. Let us the sinusoidal carrier we have, it is ct is equal to AC cos 2 pi fct plus phi c. AC is the carrier amplitude, fc is the carrier frequency, and phi c is the phase. Let carrier ct has a unit energy measured over the symbol duration tb, and so at it will be under root 2 by tb, where tb is the bit duration. And for the band pass signal, the modulated wave is defined as, st is equal to bt into ct, and bt is the incoming binary waves. So if for our conveniency we consider phi c is equal to 0, then st it will be under root 2 by tb bt into cos 2 pi fct, and the transmitted signal energy per bit it will be eb is equal to integration 0 to tb square of the mode st dt, and that here it will be equal to 1 by tb integration 0 to tb and the mode square of bt dt. And from here we can have bt is equal to under root eb. So bt is defined as, this is under root eb for binary symbol 1 and 0 for the binary symbol 0. So the bpsk signal, using this equation we can have st it will be equal to under root 2 eb by tb cos 2 pi fct for symbol 1, and for symbol 0 st it will be equal to 0. And the average transmitted energy now it will be eb by 2, because for transmitting 1 we have energy eb, and for transmitting 0 we are having 0 energy, so average it is eb by 2. So to hold this, the two binary symbols must be equiprobable. Now, ASK generation. The ASK modulator block diagram consists of a carrier signal generator, the binary sequences from the message signal, and the band limited filter. The carrier generator sends a continuous high frequency carrier. The binary sequence from the message signal makes the unipolar input to be either high or low, and the multiplier multiplies these, or you can say there is a switch and the high signal 1 close the switch, allowing a carrier signal to pass through, and the output will be the carrier signal at the high input 1. And when there is a low input means 0 bit, the switch is open, allowing no voltage to pass appear, so the output will be 0. So for the bit 1 the carrier is passed, and for bit 0 no carrier or no voltage is passed through it. And the band limiting filter shapes the pulse depending upon the amplitude and phase characteristic of the band limiting filter or pulse shaping filter. Now you can see here, this is the binary digital signal, and this is binary data 1010, and this is unipolar binary digital signal. and this is carrier, and after passing through it the filter we will have this is 1. So for the bit 1 there is carrier, and for bit 0 there is no carrier or no signal. Now ASK, or you can say BASK detection or demodulation. There are two types of ASK demodulation techniques: asynchronous ASK detection or demodulation, synchronous detection or demodulation. The clock frequency at the transmitter when matched with the clock frequency at the receiver, this is known as synchronous method, as the frequency gets synchronized, otherwise it is known as asynchronous. So first of all we will discuss asynchronous ASK demodulation. The asynchronous ASK detection consists of half wave rectifier, a low pass filter, and a comparator. The block diagram you can see on your screen. The modulated ASK signal is given to the half wave rectifier, which deliver a positive half output, and at this point you can see this is a positive half output, and the low pass filter suppress the higher frequency and gives an envelope detected output, from which the comparator delivers a digital signal as the output. Now, synchronous ASK demodulation. Synchronous ASK detector consists of a square law detector, low pass filter, and a comparator, and also a voltage limiter. And ASK modulated signal is given to the square law, and the ASK modulated input signal is given to the square law detector. A square law detector is one whose output voltage is proportional to the square of the amplitude of the modulated input voltage, and the low pass filter minimize the high frequency components, and the voltage limiter helps to get clean the digital output. Here we know AC is equal to under root 2 EB by TB, from the previous slides, or you can write it as AC square TB by 2, it will be equal to EB, the bit energy AC square TB by 2. And here this is EB is the energy in S2 in joules. So here S2 is for bit 1 and S1 is for bit 0. Now in comparator, if value is less than under root EB by 2, we decide 0 was transmitted, and if the value is greater than under root EB by 2, then we decide 1 was transmitted, and we can get a digital signal. And now if there is a white Gaussian noise error in the channel with the power spectral density n naught by 2, then the probability of error you can find out, it is a Q function of under root ED by 2 n naught, where under root ED is the distance between S1 and S2. So this is the distance between S1 S2, and here under root ED it is equal to under root EB, and you can see here S2t, it is represented by under root 2 EB by TB cos 2 pi FCT. Here S2t is the representation of bit 1 and S1t is the representation of bit 0, and here this is the probability of error, reason of error, because this is the signal of S on the identity of S1. So this is error in the decision, and here under root ED it will be equal to under root EB. So I can write Q function of under root EB by 2 n naught, and in the form of complementary error function I can write 1 by 2 ERFC is 1 by 2 under root EB by n naught, and here the EB by n naught is the signal to noise ratio SNR, because here QX, it is a function of 1 by 2 ERFC x by under root 2. So using this we can find out it will be equal to 1 by 2 ERFC 1 by 2 under root EB by n naught. So here we have computed that probability of error for ASK, it is 1 by 2 ERFC 1 by 2 under root SNR, because EB by n naught is the SNR. So here the curve between the probability of error and EB by n naught looks like the waterfall shape, and for EB by n naught greater than x2, then the probability of error less than equal to p naught, and EB by n naught can be considered as a metric that characterizes the performance of one system versus another. The smaller the required EB by N naught, the more efficient is the detection process for the given probability of error. And this curve having two system performance, and for given probability of error P naught, the system 2 is more efficient as it has less EB by N naught value, and the system 2 gives of x2 minus x1 dB SNR advantage compared to system first. So here we can see, if we fix the probability of error P naught, and if we compare the SNR value for the system first, it is x2, and the SNR value for the system second, it is x1. So here we can see the system 2 having less SNR value for the same probability of error. So this system 2 is more efficient for the detection, and the advantage as compared to system first, the SNR advantage is S2 x2 minus x1 dB SNR advantage. ASK technique is used to transmit digital data over optical fiber. That means whenever it is 1, we send some light coming from a light emitting diode LED or laser diode, and when it is 0, no light is transmitted through the optical fiber. So this is how the modulation is done. Now if we talk about the bandwidth, the bandwidth of ASK is equal to the baud rate, and it will be equal to 1 plus D into S. Here S is the baud rate or signal rate, and D depends on the modulation and filtering process, and it will be between 0 to 1, and it is very similar to AM. So we can say the bandwidth, it will be equal to 2 FM for this ASK system. And this is the end of this lecture. Here we have discussed about different special purpose line coding schemes, scrambling techniques, and amplitude shift keying techniques. This was 26th lecture of the lecture series of basics of communication engineering. In the next lecture we will discuss about frequency shift keying, phase shift keying. Till then, thanks for listening this lecture. Thank you.